Friends, thanks again for your interest in my approach to statistics and probability. Last time I did something on correlation, then midway I had some regrets. Why? Because I realized we didn't have to go so far as correlation to figure out that there's something wrong in the way people, including practicing statisticians, understand the statistical concept they're dealing with. So correlation is, say I have x which will equal x1, x2, xn. Okay, so I have a vector of n variables, and y, y1, yn. So correlation is the relationship between x and y, in other words, between each one of these observations, and what kind of cross-dependence we have, or a reflection on some kind of association between these two, x and y. But before we get there, the very same tools, just applied to x or y, are completely messed up, and we're going to see why. It's in...
Okay, so here let me just say that these x1, xn and y1, yn are data points. We call them observations. They're data points from two different data generating processes. That is why we're using different letters, x and y. So just to give an example, you can think as the x1, xn as, for example, data points on different persons regarding how much time they spent smoking. So x1 could be 2 years. Person 1 spent 2 years smoking in his life. x2 could be 3 years. So these are usually real numbers. These x1, xn, they're data points. And y1, yn could be, I don't know, how much lung cancer, a measure of how much lung cancer these people have at 60. Okay, so when you have two data points from two different data generating processes, you might want to understand if one is dependent on the other. So in statistics, you can calculate correlation, which is a measure of linear dependency between two sets of observations. Now, the point here is that we're not going to deal with correlation in this video, so no mind this. But some of the same problems Professor Taleb has with correlation, he has also with standard deviation, but is a measure that can be calculated only on one set of data points from one single data generating process. This is a measure of variability, and some of the problems that Professor Taleb has with correlation can be seen even with simpler measures like standard deviation.
A lot of the stuff is in my statistical consequences of fat tails, chapter 3. I think chapter 4 discusses this problem with standard deviation, because standard deviation only works, okay, the metrics we use for x is standard deviation. So let's talk about SDB, the metrics, and the metrics used just for one variable in one dimension. So the first problem is that if I tell you, define standard deviation, most people have the perception that standard deviation means how much something moves on average every day. And we quizzed people, just to tell you how misunderstood these concepts are. People can write down on paper what they mean. And when you quiz them, as has been done by many decision scientists, they explain something else. So you ask people, what is standard deviation? And they tell you how much something moves about on average every day. We found it on websites of government agencies, this definition. The Economist, of course, you can always look, if you want a wrong definition, in the Economist. So standard deviation is not how much something moves on average. Standard deviation, I take x1, x2, x3, xn, okay? I take the average, x bar, and then what I do is I take the sum of xi minus x bar square. That's what's critical 1 over n, and I take the square root. You're squaring the deviations. Now, when you square the deviation, you're going to give much larger weight to large observations and smaller weights to small observations. So most people have the feeling, you write down standard deviation, that's sigma, okay? That this, okay, mentally equals this. I take xi minus x bar, 1 over n. That's what people have in mind. Maybe there's a little bit of light here.
Okay, so let me just stop here and give you a very quick catch up on what we do in statistics. This is going to take a little bit, but we're going to use it even for further lectures and even for this one. So usually we denote observations like this. So these are data points, x1, and these are n data points, big N. And in statistics, we want to model phenomena stochastically, randomly. So that means that to each outcome of a possible data generating process, we're going to assign some probability. For a very simple example, here we have what we call a Bernoulli distribution. So to assign probabilities, we use a function that is called the probability distribution, and this is just a function that assigns to each outcome a probability. So let's go back to the simple example. Here the Bernoulli distribution is very, very simple. We only have two possible outcomes, and think coin flips, for example. So this could be we could be modeling the flips of a coin, and 0 could represent heads and 1 could represent tails. And so in this example of a probability distribution, the probability distribution would be assigning 60% probability to heads happening and 40% probability to tails happening. Okay, so here we're just repeating that probability distribution is a mathematical function that assigns probabilities of occurrence of different possible outcomes for an experiment or data generating process. Like in this case, it would be coin flips. Now, let me just say that this is one way to proceed to model physical phenomena, but one could think about a more classical physics kind of way of modeling things. So, for example, if you think about coin flips, one could measure the angle at which one is flipping the coin, the temperature in the room, the trajectory of the coin, to try to determine through these variables deterministically if the coin is going to come up heads or tails. In statistics, we take a different approach. So the outcomes of an experiment are always going to be assigned some probability. And we do this through probability distributions. Lovely. So the axioms we want for these probability distributions to make sense to us as humans is that the sum of all the probabilities of the different outcomes has to be equal to 1. We don't understand what it means for probabilities of 120% of occurring mean. So the sum of all the probabilities has to equal 100%. Then we want probabilities to be positive. We don't really understand what negative probabilities mean. It's not intuitive to us. So these are the axioms we impose on our probability distributions. In the case here, we have a discrete number of possible outcomes. So we call these probability mass functions. Now, not every data generating process comes in discrete outcomes or finite number of outcomes. So for example, think about me going down the street, looking at people's heights and then noting them down as a data point. Then the heights of people come in a continuum of values. There's not only two heights, there is an infinite number of heights, an uncountable infinite number of heights. So one can be 1 meter 80, 1 meter 80 and a few millimeters, etc., etc. So when we are in this scenario, then we still are going to use a probability distribution but we call this a probability density function. This is just some jargon, some statistical jargon that I'm just throwing at you right here. So we still have a smart way to assign probabilities to an uncountably infinite number of outcomes, and we do this through a continuous function that integrates to 1, because we're going to assign the probability that a certain outcome happens as the area under the curve. So just to give an example, let's say A is 1 meter 60 and B is 1 meter 90. Then the probability that in the previous example, I observe a person that is going to be between 1 meter 60 and 1 meter 90 is going to be equal to the area under the curve of this probability density function. So this is a smart way to assign probabilities to outcome even when there's an infinite number of them. You can think about the integral as a generalization of a summation. So we're just inheriting these, let's call them axioms, from the discrete case to the continuous case. So we want probabilities to be positive for every x, and we want the integral to sum to the whole area under the curve to be equal to 1. Now, great. Now, once we have a probability distribution, we like to calculate some properties of a probability distribution. So, for example, we like to know what is the mean value of a probability distribution. The mean in the discrete case, we call this mu, this Greek letter you see here. Excuse me. And this is just a weighted sum of all the possible outcomes times the probability of that certain outcome happening. Now, along with a measure of the mean, of the average, we like to compute measures of variability. This is how spread is the data going to be, how spread out is the data going to be if I choose a certain probability density. And then we define standard deviation. Standard deviation, we use this letter here, sigma. And we take a square root of a weighted sum of square differences from the mean. So why is this intuitively a measure of variability? Because we're taking differences from the mean and then squaring them. So if a probability density is going to have larger, large amounts of density that assign. Okay, so let me repeat this. So if probability density has large amounts of density. Has density that assigns large values of x to outcomes far away from the mean, then this quantity is going to be greater. So if density is going to be more spread out, then this quantity is going to be greater. And here we have the continuous versions of these quantities for probability densities, and these are for probability mass functions. I just call them probability distributions. If I sometimes mix it up, it's because I just call them probability distributions. Anyway, so there's another measure of variability one can compute on a probability density, and this is the mean absolute deviation. But this is not very used by statisticians and by applied statisticians. So we always ubiquitously use this quantity here. This is the quantity we all use. But there's another one that's mean absolute deviation, and the intuitive reason why this is a measure of variability is the same as this one. We are calculating differences from the mean and then taking a weighted sum of them with the probabilities of these respective outcomes of happening. Here, notice that we don't take the square. Okay, lovely. Now, I have to introduce this probability density because it's the most famous probability density. We know everything about it, and we like to use it because it's convenient mathematically. It makes things simpler for statisticians and applied statisticians. And this is the Gaussian distribution, also called the normal distribution of a bell curve. So this is a probability density function. You can see it here in black. And this is the mathematical equation that gives you this function, if you plot it. You see we say parameterized, so there's two real numbers that define it, and these are called sigma and mu. These are not called sigma and mu by chance, because if you compute the mean of this probability density, it's going to spit out exactly mu. And if you're going to compute the standard deviation of a Gaussian probability density, then it's going to spit out exactly sigma. So we don't give these. We don't use these symbols by chance. We use them to mirror what we defined before, because these are actually going to represent exactly the quantities we defined before. Notice that for the Gaussian, this is another reason we like to use it, but there's more deep and profound theoretical reasons we're not going to get into right now. But one of the reasons we like to use it is because the mean and the standard deviation characterize the whole distribution. Once you know those, you can plot the entire normal distribution. So if you have data that comes in a histogram like this, you might want to use the normal distribution to model it. Okay, so now this is a crucial point. So now what happens in the real world? So what happens in applications? Well, we don't know a priori. We don't know what density a certain data generating process has. The only thing we have is that we can observe data points. We can observe a number of data points. And then if we want to use, if we want to assign probabilities to the outcomes, we have to fit some probability density to, we have to model our data generating process through some probability density. But we don't know if we're going to choose the right one. The probability density that we choose to model a certain data generating process could be mistaken. So for example, I could choose to utilize a normal distribution to model coin tosses. And that would seem quite dumb, a quite dumb thing to do, but I could do that, and then I could try to fit the normal distribution to single coin tosses. But yeah, I'm trying to drive home the difference of what the data generating process has a certain probability density, and then you use a model to approximate that. And this is why statisticians sometimes say that all models are wrong, but some are useful. So once we have a set of data, let's say we want to fit a probability distribution to it to continue to model data statistically. And then we can compute some estimators for some of the quantities we defined before, the mean and the standard deviation. So this is the sample standard deviation. So you compute this with the data points, and it's an attempt to estimate sigma as defined before. So here first we define an x bar as the sample average, the sample mean given our data. This is just a sum of the data divided by the number of data points. And this is what Professor Taleb wrote on the blackboard without writing explicitly this formula. And then here is the sample standard deviation. We're not going to talk about if this is a good or bad proxy for the standard deviation. Just let me give you an intuitive explanation of why this might be a proxy for this quantity here. So first of all, you can see that they're quite similar in their definition, but you might notice that there's no probability in the equation. So there's no probability because, as I was saying before, you don't know the probability of a data generating process, so you can't use it. But why is the probability somehow underlined, somehow implicitly in this formula it is used in some sense? It's because as n increases, so as the number of data points increases, the ones that are more likely to occur are going to occur more than the ones that are less likely to occur. So when we take these averages, let's call them like this, in some sense will approximate the probability of a true data generating process. Now, this is just an intuitive explanation, just to give you an idea of why we might choose these kinds of estimators. So, as we can estimate the mean and the standard deviation, we can do the same thing for the mean absolute deviation. And this is a quantity, would be an estimator for the mean absolute deviation. This is always calculated with the data. So let me just give you an example here for people who might be just starting to do these things. So say we have 4 data points. We can think about these as heights, so 1.90 m, 1.60 m, and so on. Then the sample mean would just be the sum of these values divided by the number of observations, which is 4. We have 4 data points, observations, which go to 1.73 m and something and something. And then when we calculate the sample standard deviation, we again have a sum of 4 quantities. This time these quantities are squared. Then we are dividing by 4. So this is the way this formula pans out in practice. And we can do the same thing for the sample mean absolute deviation. Okay, and in general, we know that the mean absolute deviation is always going to be less than the standard deviation. This is a theorem or a mathematical lemma, if you want. Okay, so the point, now to reach the point, finally we can reach the point that Professor Taleb was talking about. So in practice, everybody is computing this, but what they think about intuitively when they compute this is this quantity here. So we compute this because we love the standard deviation and we want to measure variability. But actually, when we compute this, we forget that we're taking squares here. We're taking this square and this square root because it's not very intuitive to think about we're assigning more values, we're assigning greater value to deviations that are very far away from the mean, and then we're increasing their magnitude by squaring them. Instead, we intuitively think that we're doing this. But these two quantities are very different. The mean absolute deviation and standard deviation are 2 different quantities. So let's hear what he has to say.
Creating a shadow. Okay. So they mistake this one for this one. This is the mean absolute deviation. And actually, the ratio between these two corresponds to fat tails. For the Gaussian distribution, sigma over mean absolute deviation equals square root of pi over 2. Okay, that's for the Gaussian. Most other have higher, which is about approximately 1.25. Most distribution, of course, fat tails higher, and this goes to infinite when you have a power law distribution with a tail exponent higher than 2. Okay.
Okay, so let's unpack this. And this is quite dense. The signal to noise ratio is quite high, so there's a lot of signal and little noise. So let me just say before this that I'm using this notation that is not standard, this sample mean absolute deviation, but I'm just trying to fix in mind that one thing is the quantities we compute with the data points, and the other thing is the quantities we compute with the probability densities, or the probability distributions, better. So Professor Taleb is pointing out that even in the case of a normal distribution, when we compute the mean absolute deviation, here's a proof, you don't need to understand this, don't worry. When you compute the mean absolute deviation, it comes out like this. So the square root of 2 over pi of a standard deviation. So the mean absolute deviation and a standard deviation, even for the case of a normal distribution, are different objects, are different quantities. And moreover, if you take the standard deviation over the mean absolute deviation, so if you take it here, the result would be only square root of pi over 2, because the standard deviation would cancel out with the standard deviation at the numerator, and this would flip. Then if you calculate the standard deviation over the mean absolute deviation, this is going to be a measure of how fat the tails of a distribution are. And I'm going to give an intuitive explanation of this fact, but first let's talk about the thickness of the tails, or what does it even mean for a probability distribution to have fatter tails. So here we have two probability densities. The one in light green is the normal distribution, which we have already talked about. And the one in dark green is another probability density that has fatter tails than the normal distribution. And so this one in dark green approaches 0 as a polynomial, while the normal distribution is defined through an exponential, so it approaches 0 as an exponential, and exponentials go faster to 0 than polynomials. So just heuristically, there are technical mathematical ways to define what fatter tails are, but just heuristically, you think about a distribution has thicker tails than another one if it assigns higher probabilities at the extremes. If it is assigning higher probabilities to the outcomes that happen at the extremes, then we can heuristically think about a probability as having fatter tails than one that does not assign as fat as big a probability to extreme values happening. So in this case, the green one, since after this point onwards always stays above the normal distribution, has fatter tails because it's going to assign more probability to extreme values. We're going to talk about these a lot, so just this as a first explanation I think is decent, just to understand what fat tails mean. Anyway, now why is the ratio of the standard deviation to the mean absolute deviation a measure of how fat the tails are, a proxy for how fat the tails are of a distribution? Well, as it says here, the standard deviation gives greater emphasis to large departures from the mean because we are taking the square. Because when we compute the standard deviation, we are taking that square, outcomes that are very far away from the mean are going to be assigned an even greater magnitude after they're squared than if you only take the absolute values. Now, if there are large departures, these large departures are at the tails, thus the standard deviation will be bigger than the mean absolute deviation for fat-tailed distributions. So this should make sense to you. And this directly implies that the ratio of standard deviation to the mean absolute deviation is going to be an indicator of how fat-tailed a distribution is. This is just an intuitive explanation of this fact. Okay, great. So the point was that not only the mean absolute deviation and standard deviation are very different things, but we'll shortly see that the standard deviation can even explode while the mean absolute deviation remains constant. So it's a big error to conflate these two quantities, and their ratio is a proxy for the thickness of the probability tails of a probability density or of a probability distribution.
So now you wonder, and I wrote this chapter and I said it, in expressive term, why the fuck did we use standard deviation? Since what people have in mind is mean deviation. Why? It leads to aberration. Let me show you the aberration. I mean, when mentally someone asks you how much the temperature change wherever you live, say you live in the southern section of Palermo, Sicily, presently in the Republic of Italy, someone asks you how much does temperature change, what do? You take the deviations, you square them, take that average and take square root? No. You say, well, the other day it changed by 5 degrees, and then you had 8 degrees, and then you had 7 degrees, I averaged them. Okay. So that's how you work.
So here, Professor Taleb has just given an intuitive explanation of why, as a measure of variability for us humans, the mean absolute deviation is much more intuitive, and why we tend to think about this. Because if we have differences of temperatures and we want to understand how much these temperatures are varying from one day to the other, we're just going to take the differences and then take the average of the differences. We're not going to square and then take the square root. It's just a bit more complex, a bit more involved.
You don't square. That notion of squares is what really has fucked up statistics quite a bit. That it worked for Gaussian. Even then, we're not that sure. So let me show you, for example, where mean average deviation doesn't map to standard deviation. Let's take 0, 0, 999,999. This is the deviation. And then you have a million. Okay, so you have a million observations. All of them are 0 except for one. It's a million. Okay. Compute standard deviation. Standard deviation is going to be about 1,000. And what is mean absolute deviation? It's going to be 2. So sigma over mad is going to be 500. So sigma is going to be 500 times the average deviation. Why? Because think about it. You're squaring. These have no weights. It's like a weighting operator in which you have more weights on large deviation and no weights on small deviation. 0, the things close to the mean, which is 1, have no deviation.
Okay, so let us see this toy example Professor Taleb is proposing to us in a bit more detail. So this is just going to be a toy case in which we can compute all these quantities quite quickly, and we can see that the mean absolute deviation and standard deviation can be very, very different. So let's start small. So anyway, we're going to take a probability distribution that has equal probability to end up in any state, and there's going to be n of these states, little n of these states. And for the first n-1 states, we're going to say the outcome is going to be 0. We're going to assign the outcome 0. And then in the last state, we're going to say that the value of the outcome is going to be n. So so here we're using states as a synonym for outcomes. Okay, that's okay. Just keep that in mind. So if we had 2 states, then what would be the outcomes of our probability distribution? Well, the first n-1 ones that would be just 1 would have value 0. Then the second one would have value n, but n in this case is going to be 2, so it's going to be 0, 2. And this would just represent Bernoulli distribution as the one we saw for the example of the coin flips, where instead of the outcomes having values 0, 1, they have 0, 2 here, but those were just labels. So it would be a Bernoulli distribution. We would have 2 outcomes and we would assign equal probability in this case to both outcomes of happening. Now, if we have n equal to 3, which should be little n, then we would have 3 outcomes. The first 2 would be 0, and the third would be equal to 3 because n is equal to 3, and so on and so forth. So we can construct this sequence of probability mass functions in this case, and we can first observe that as we go along constructing these probability mass functions, the tail is going to increase, in the sense that there's going to be a number of zeros for the first n-1 terms, and then there's going to be a big value right here, far away, at the extreme of this probability distribution function. And so as n increases, the bigger the tail is going to get. Now, we notice that for any n, all these probability distributions we are constructing have all mean 1. Why? So let's first go by cases. So in the first case, so to the first outcome, we assign in probability 1/2 because we're assigning equal probability to all outcomes, and there's only 2. So 1/2 times 0 plus 1/2 times 2 is going to be equal to 1. And this probability distribution is going to have mean 1. Now, if you go here and let's calculate the mean, then it would be 1/3 times 0 plus 1/3 times 0 plus 1/3 times 3, which is going to be equal to 1. In the case where we have 4 outcomes, you can understand it's going to be the same thing. So 1/4 times 0, 1/4 plus 1/4 times 0 plus 1/4 times 0 plus 1/4 times 4, which is going to be equal to 1. Okay. So if we want to compute the mean absolute deviation now of the nth distribution we are constructing, then this is just a definition. So what would we do? We notice that the first n-1 terms of this summation, this x for the first n-1 terms of this summation, this xi is going to be equal to 0. The mean we said is equal to 1. So here we're going to be summing n-1 ones. The sum of n-1 ones is going to give us n-1. Then we're going to multiply it by this quantity, which is always going to be equal to 1 over n by construction, because we're assigning equal probability to all of the outcomes. And then the last term of this summation is going to be xy is going to be equal to n, this is the last term of the summation, minus 1, always times 1 over n. So this is going to be the last term, n minus 1 again. Okay, so lovely. So it's easy to compute the mean absolute deviation in this example. And then we can even compute the standard deviation. And for the same reasons, here the first n-1 terms are going to be equal to -1. Then we're going to take the square, which is going to give us 1. So the summation is going to be, the first n-1 terms of the summation are going to be 1s. So the summation of n-1 ones is going to give us n-1. And then for the last term, here we're going to have n, here we're going to have 1, so we're going to take the square of n-1 squared this time. So when it's all said and done, this is going to be equal to square root of n-1. Now, we can notice now that we've computed both these quantities that as n increases, so for example, Professor Taleb takes n equal to 1,000,000, then the standard deviation is going to explode. It's going to become really large, and while the mean absolute deviation is just going to tend towards 2, because this quantity is going to become very small, and this is going to remain the same. So as n goes to infinity, the mean absolute deviation is going to be 2, and the standard deviation is going to explode. So the bigger we make the tails, all the way over here, the bigger the standard deviation is going to get, but the mean absolute deviation is going to remain quite stable instead. So again, we're driving the point home that the mean absolute deviation and the standard deviation are two very different things. And the ratio is an indicator of how fat are the tails of a certain probability distribution. Lovely. So thank you for this nice example. Let me just say that here he's just approximating the mean absolute deviation with 2. So don't worry about that.
Realize the absurdity of it. It doesn't matter anything. I worked out the math to show you the distortions in it, in statistical consequence of fat tails. But then, just wonder, why do people use standard deviation? For a Gaussian, it makes sense, because about 67.8% of the observation fall between -1 and +1 standard deviation. Okay, you may say so. Standard deviation allows us to do some limit theorems when it comes to probability theory, okay? And when you want to derive some stuff, some results, okay, that's fine. You don't need it. So, the strange thing, and you can try it, take data, Let me show you that standard deviation isn't a metric that is very intuitive. Let's say around x, mean is 0. So you have observations, positive observations and negative observations. Take the negative standard deviation and take the positive standard deviation. And you'll see it's not additive. You're going to have half of the positive, half negative. The negative standard deviation plus the positive standard deviation will not map to the total.
Okay, so here this is an other counterintuitive fact regarding standard deviation. What Professor Taleb is pointing out is that if you partition your data in two different sets with no overlap, and then you compute the standard deviation of one of these groups, and then you sum it with the standard deviation of the other group, this is not in general going to be equal to the standard deviation computed on the whole data set. Okay? So let's take the example we had before, just to confirm that this fact is indeed true. So this was the data set we had before, and let's compute the sample standard deviation only on the first two observations. Then we would have this quantity here, while if we compute the sample standard deviation on the observations 3 and 4, then we would have this quantity here. Now notice that this is the sample standard deviation computed on the whole data set, which we have already computed before. And this quantity, this number, is going to be less than the sum of the standard deviation computed on the two partitions, on the partitions that we made of the data, the first two ones and the third and the fourth. So again, this is a counterintuitive fact about standard deviation, that mean absolute deviation doesn't have. So if we were to redo these calculations with a mean absolute deviation, we would get the same number calculating the mean absolute deviation on partitions and on the entire data set. This is because the mean absolute deviation is just a sum of differences. So immediately from the definition, we see that the mean absolute deviation behaves as expected. So again, this is just another peculiarity, another property that is counterintuitive of the standard deviation.
Try it, and you'll see that it's not additive. So before getting into correlation, what is correlation? Correlation is pretty much the scaled, we take the covariance xy over STD of x, which is basically square root of the variance of x, and the STD of y. So we're already starting off with a metric here that doesn't correspond to what you think. When we'll discuss correlation again, I will show what people have in mind with correlation.
Okay, so here the point that is being made is simply that correlation is defined through standard deviation. So if we don't understand standard deviation very well, if standard deviation is counterintuitive to us, then the implication is that correlation is going to be counterintuitive to us because it's defined through standard deviation. Now, we're not going to write down correlation now because anyway, we're going to talk about this in further lectures, and we're just going to say a little thing, but this was just the point being made right now.
Typically, is mentally, they look at something called the beta, which is going to be the correlation x, y, over rho x, depending on what you use, x over rho y, or depending on what you're looking, how you're expressing your beta. And this normalized, of course, will be 1. So people will have in mind this metric, and we show that it fails in a nonlinear environment. Thank you. Thanks a lot for listening.
Okay, so here just for the last point is that as people, when they compute standard deviation, have in mind the mean absolute deviation. So they have something else in mind. in the same way, when people compute correlation, they have in mind this beta quantity that Professor Taleb wrote on the blackboard, which is not correlation, it is something else. So he is just drawing a parallel between the initial point that standard deviation is not what we usually, it's not a measure of variability that we usually think about. So we're usually thinking about something else. Okay, so these points are just little remarks that we will discuss more in further lessons.
And have a great day.
Okay, let me just say that if you didn't understand, don't worry. Of course, we're going very quickly, and I'll put a link of the writings I was using just somewhere here in the description, I guess. Thank you very much. Thank you very much for listening.